I'm here with Bogdan Wyda, and he is from the Jet Propulsion Laboratory. And Bogdan, we're talking about opals, but it's not the kind that I like, I don't think. Let's talk about your
That's right.
research.
That's right. We're not talking about the actual gemstones. We're talking about the optical payload for laser comm science. And we're trying to do is put a laser on the International Space Station and perform a technical demonstration of optical communications. And currently in space, the way they communicate between spacecraft and the ground is through radio waves, much like you get the radio in your car. Laser communications, for a couple of reasons, is able to generate much higher data rates than conventional RF radio. So for the same amount of power that is required, you can get data rates that are sometimes 10 to 100 times faster than you can with radio frequency. Our particular payload is actually trying to do something that's relatively modest by optical communication standards, and that's because the focus is not so much to show that we can do high data rate, but rather to show that we can do optical communication. So the sort of rates that we will be getting is about 10 to 50 times faster than what you would get at home in your typical cable internet. And we'll be using a laser that's about 500 times more powerful than this one. This is about 5 milliwatts of optical power. Our laser is about 2.5 watts of that, and that's what allows us to achieve these sort of data rates.
So how does it work?
So the concept itself is fairly simple. Enacting it is the challenging part. So as the ISS flies over our ground station in California, our laser will essentially try to keep the spot pointed to our ground station. And to give an analogy, it's the equivalent of me trying to use this laser to point to an area that's the diameter of about a human hair from about 20 to 30 feet away, while I'm moving at about half a foot per second. So
that's precision right there.
That's right. It's all about the precision, and that's really the most difficult part about optical communication is the pointing, because the beam is so narrow.
So what do we gain on Earth and in space from learning about this?
It helps. It increases future missions' ability to bring back more science data for the same amount of resources that you put in. So in low Earth orbit, the upcoming Earth science missions are generating data at rates that are much higher than we are able to bring them down. We're approaching that point right now. And so optical communication can offer a relief and allow us to bring down much more data. For deep space, it has also deep space applications. So if you think of a Mars mission, for example, you could have a satellite in orbit about Mars that is able to transmit much higher data rates, about 40 times faster than we currently have available.
Wow. So when are we going to see this laser from the station?
Opals is currently scheduled to launch in 2013, so if everything goes well, that's when we will be going up, and we will be operating for about 90 days. And if everything goes well, hopefully even beyond that.
It will go well, I know it. Thank you, Bogdan.
Thank you.
This is Mission Control Houston. Again, that was a look at the upcoming Opals experiment that will be flying up to the International Space Station coming up later on this year. If you would like to learn more about it, just log on to the NASA website at www.nasa.gov/station. There's a feature story there on it.